This is Liu Liu from Tsinghua University. I'm happy to present our work, INS-Conv, Incremental Sparse Convolution for Online 3D Segmentation. Online 3D semantic and instance segmentation is highly demanded in applications like robotics, autonomous driving, AR, and VR. Current online 3D segmentation often use 2D-based methods, which cannot utilize global information, thus suffer from low accuracy. The high-precision 3D segmentation methods often adopt 3D convolution, for example, the submanifold sparse convolutional network, but they require to input the forcing, which is too slow to apply in online setting. Our work is based on sparse convolutional network. We first give an introduction to it. The sparse convolution only calculates for active locations, which contain non-zero data. This accelerates the computation. The submanifold sparse convolution is further proposed to constrain the output active locations to be the same as the input active locations, to avoid data dilation. This method, however, is still slow and takes 2 seconds to process 2 million points. Our insight is based on the following property. A linear network satisfies fx plus y equals to fx plus fy. At time t, we decompose the current propagation fxt into 2 parts, fx t minus 1 plus f dx. xt means the current thing, xt minus 1 means the previous thing, dx means the residuals between xt and xt minus 1. fxt minus 1 has been calculated in previous time. We only need to calculate fdx. dx here is very sparse. Here is the overview of our method. We calculate the residuals of things by our INS-Conv backbone. It propagates residuals of features, which is fast and accurate. The output is the result of the change points. We fuse these results into global results to get the current segmentation map. We design layers on top of sparse convolution to propagate residuals of features. The INS-SSA layers perform submanifold sparse convolution on residuals, which constrains the output residual locations to be the same as the input, as shown in Figure C. More layers are described in our paper. We use a typical 3D ULET sparse convolutional network as backbone. For each input voxel, it outputs a semantic probability for semantic segmentation and an instance embedding for instance segmentation. At training time, it performs like standard submanifold sparse convolutional network. At inference time, we replace layers with corresponding INS-Conv layers to propagate the residuals. At each time t, we only get the results of the change points. Therefore, we need to fuse these results into global results to get the current segmentation map. For instance segmentation, we compare similarities between current instances and the global instances by mean embeddings to match them. For semantic segmentation, we fuse the current point probabilities to global by weighted average. We perform Ablation Study to test the effectiveness of INS-Conv. We compare the results of directly calculating the current change points and the results using INS-Conv with the same amount of input data. The accuracy is increased by a large margin. This is because INS-Conv utilizes the global information. Besides, INS-Conv achieves nearly the same results as full propagation. We compare INS-Conv with other online and offline 3D segmentation methods. The results surpass all previous online methods and are on par with state-of-the-art offline methods. Here gives some qualitative online segmentation results. We perform runtime analysis. The runtime of INS-Conv is irrelevant of the size of the scene and achieves more than 10 FPS, while the runtime of offline methods increases with the size of the scene grows. Here is a demo of our system. We use a portable device without the use of GPU. Our instance segmentation map is temporally consistent. This is the end of our presentation. Thank you for listening.